of Cassandra being open source. And so what we've been working on for the last, about the last year has been to kind of take stock of where we were and what we've achieved and what we need to change to make Cassandra easier for a mass market audience. So those of you who've seen me speak before have seen a slide like this. Cassandra's core values have been scalability, availability, and reliability, and performance. And we really were the best in class at all of these core values. To drill down a little bit into performance, last year there was a group of researchers at the University of Toronto. They benchmarked the leading NoSQL databases, and Cassandra was far and away the leading contender. They had benchmarked half a dozen different workloads. This slide is reads, writes, and sequential scans all mixed in together. But across all the different workloads, Cassandra was at the top. That benchmark was great, but it actually didn't cover MongoDB. So when a lot of people, Tenjin's marketing department has done a great job. When people think of NoSQL, a lot of people think of MongoDB. So DataStax actually commissioned a company called Endpoint to kind of add MongoDB to this benchmark. And so we actually used the same YCSB benchmark suite that the University of Toronto guys did. And you can see the kind of the yellow and blue lines here, Cassandra and HBase, are basically the same distance apart as they were on the VLDB benchmark. So Cassandra is about 3 to 4 times as fast as HBase. So we're seeing kind of a consistent, repeatable result. And you might notice that instead of being a straight line, this one's kind of curved up. That's because instead of adding a constant number of nodes to the cluster on the x-axis, we're actually doubling the cluster size at each data point. So we got to a slightly larger cluster to show that Cassandra is still scaling linearly. But far below Cassandra and HBase, you have MongoDB bringing up the rear. And this was actually true as well across the different workloads, which surprised me a little bit because conventional wisdom says, well, MongoDB has this document level lock, and so it slows way down when you mix writes in, but it should be really fast for reads. But actually, it was basically the same ratio of slowness for reads as well. So go figure.
What's the y-axis?
Operations per second. And these were, I believe, 1,000-byte records or documents. And we've been seeing an increasing number of Cassandra deployments and people being able to not just test it out in a development environment, but actually have it out there in production, see what that does for their reliability. In the lower right-hand side here, Jake Luciani deployed Cassandra 1.2. One of the big features there is Cassandra has greater awareness of what's going on with its disks. So if a disk starts erroring out, Cassandra can blacklist it, or it can just shut down the server process. So Jake's out there saying, this saved our cluster a bunch of times over the old 1.1 behavior, which was just sit there and spew out errors until somebody notices. So we've been making progress in a bunch of different areas, but the big one that I think we've been missing has been ease of use and developer productivity. So we've been working on a Cassandra query language, which is effectively a subset of SQL, for about 2 years now. And so at the beginning of this year with Cassandra 1.2, that was where we said, okay, it's ready for production. And we've been solidifying that with 2.0 coming up basically probably in about a week. We launched the 2.0 release candidate 2 today, and so probably in a week to 10 days we should have the final release out. I don't think we're going to find any showstoppers at this point. So we have people, again, we launched 1.2 at the beginning of this year. We have a number of deployments in production that are using it and have proved it out. Because again, this is the culmination of several years of work. So we've had experience, time to iron the bugs out. Under the hood, we call the version of CQL in 1.2, we call it CQL3, because we had a couple revisions of the language that didn't quite measure up, it didn't quite accomplish what we needed it to. But with 1.2 and CQL3, CQL can do anything Thrift did better and in a much more productive fashion. So we've already got documentation of this on the DataStax side. If you just search for CQL in the documentation, you'll come up with this pretty good introduction. I'm going to go over a little bit of that today, starting with what we added in 1.2 and continuing into 2.0. So I'm going to gloss over just a little bit the first bullet here, the Thrift compatibility, because it's a little bit hairy. But the takeaway is that, yes, that CQL can read any data that you had in a table that you created with Thrift. So this is actually, it's actually much easier now in a lot of ways for people to learn Cassandra starting from scratch with CQL than for people who are coming from the old Thrift-based paradigm to kind of wrap their minds around CQL, because we're asking you to unlearn some things. But the answer is yes. And so I've actually had 3 separate attempts to explain how this backwards compatibility works. And I think we've finally got it to where people like Ed Capriolo have figured out and wrapped their heads around what we've done here. So like I said, I won't belabor the point here other than to say yes, it is compatible. So we've added some things in CQL, and this is one of the reasons we were pushing in this direction that weren't possible with the Thrift API. So one of these is collections. So this is kind of standardizing a design pattern that you have in Cassandra that you want to denormalize at update time, so that when you go to read the data, you can just do a simple fetch from a given row or a given partition of rows and do that very performantly. So denormalization is kind of a first-class concept in Cassandra, but we didn't really give you any tools to make that easy. So you basically had to roll your own at every step. And so collections is a first step towards standardizing this pattern. So as an example of what I would use this for, suppose I have a users table and users have multiple email addresses. In a relational system, I'd create a one-to-many relationship between users and email addresses, and then I'd pull those out with a join at runtime. So in Cassandra, we don't allow you to do that. We don't allow joins in CQL. But what collections let you do is it allows you to say, okay, I'm just going to have a column here that's actually a multi-value collection. It's a set of email addresses. And besides sets, we also support lists and maps. And so you can manipulate that using set literals. So here, the plus operation is basically unioning the sets together. If I didn't have if I had just this set literal without that would blow away whatever existed previously and say this is the new value of the set. So you can either append incrementally, or you can just say here's the new value of the set. Both of these are efficient operations in Cassandra. So there's actually some superficial resemblance to what you see in document databases like MongoDB or React or CouchDB, where you have these kind of nested structures within your row or within your document. One of the big differences with Cassandra is that updating this is an efficient operation. I don't have to rewrite any data that's in the rest of the row or in the rest of the collection. So all the document databases that are built on kind of a key value storage engine under the hood, they're going to require read the existing row or document, modify the collection, then rewrite the entire thing back out. So under the hood, Cassandra is more efficient here. As part of making CQL a first-class citizen, we had to expose some of the internal knowledge that Cassandra has about itself and about the cluster that under Thrift we'd exposed with kind of one-off methods. So we had describe schema and describe key spaces and describe ring. These methods, we needed to expose those in a way that you could access them with CQL without needing to fall back to Thrift. So that's the motivation behind the data dictionary, which is in the system key space, and then we have a bunch of column families within that key space that contain Cassandra's knowledge about itself. So the local column family is my knowledge about the local server. Peers is my knowledge about the cluster. The tables that start with schema are the schema definitions, and so forth. One of the other things that we did for 1.2, and this was actually, I think, in either 1.2.1 or 1.2.2. So 1.2, as you'll see as I'm going along, it was a little bit of a creeping feature release where we slipped some things in as we went along that we didn't want to wait all the way for 2.0 for. So relatively early on in January, we added authentication to 1.2. And this is what that looks like using CQL. You basically have create, alter, list, drop users. And this is all basically Cassandra's hashing the passwords and storing them internally out of the box. So the default behavior is for this to be commented out. There's no authenticator. Cassandra allows everyone to do everything. There's no login required. That's the default still. But you can uncomment password authenticator, and then users have to have accounts created and log in with the appropriate credentials. For DataStax Enterprise, we also offer, and by we I mean DataStax, also offer a Kerberos authenticator that allows you to plug into an enterprise single sign-on solution. But we open sourced all of the password-based authentication and the integration of that with CQL. Now, I should note that I've kind of illustrated here a best practice when enabling the password authenticator, because to kind of bootstrap authentication, it creates a super user, username Cassandra, password Cassandra. So leaving that around, not a very secure idea. So what you can do is you can create another user with that's a super user, and then you can drop the original one, or you can change the password on the original Cassandra super user. So either of those approaches is fine. So for authorization, we also support granting roles and privileges to those users that you've created. So select, modify, and then you can nest those permissions across key spaces, across tables, and so forth. So fairly straightforward. Yes?
What sort of performance impact do you have if you have all that turned on and you're doing the authorization per table?
It's fairly negligible, because once you've accessed a table, it will cache your permission on that, and then it won't need to go through and requery, reload the permissions map on every request. So it will cache that for the lifetime of your connection. So it's basically a couple hash maps lookup of overhead per request. So generally speaking, your bottleneck is going to be elsewhere. And thank you for reminding me, by the way, we do have a relatively small group, so just go ahead and raise your hand or yell out a question as we go along. You don't need to wait for the end. I think that'll work better with this group tonight. So as part of this development of CQL, we've concurrently been developing a native protocol for CQL clients to access Cassandra without having to use Thrift. So this gives us a couple benefits. One of which, and made pretty high on our list of motivating factors, is that when we design our own protocol, we can make it asynchronous. So we can have the server push notifications to the client. And so one of the reasons you want to do that is that since you have a cluster of Cassandra nodes, when I add new machines to my Cassandra cluster, I want my clients to know about that so they can start load balancing across the new ones as well as the old ones. So under Thrift, the Cassandra clients would have to poll the cluster on a regular basis, saying, hey, what machines are in the cluster? Hey, what machines are in the cluster? And so now we can just push that out to the clients that are connected and say, hey, here's the new machines. Or we can go further, and we do go further and say, oh, this machine is dead, take him out of your rotation. Oh, he's back up, you can put him back into the pool. So you can start to do more sophisticated things like that. We also get the benefits of having prepared statements being first-class citizens in the protocol, and we could make that that much more effective, that much more efficient on the wire. So it's very, very efficient now to execute a prepared statement over the native protocol. You basically just say, here's my prepared statement ID, here's my bind variables, and then you get back your results without having to go through the whole metadata about the request that you would have to do in Thrift. So we have the Java driver generally available. The .NET and Python drivers are beta, and people are using these in production. So it's beta, but fairly robust beta. And we're also working on PHP and Ruby drivers internally at DataStax. And we're working with people in the community on drivers for things like Go and Erlang and C++ and so forth. Another thing that we did in CQL is give you a lot more visibility into what's going on under the hood through a tracing framework. And so what you can do here I've got an example output from SQL Shell. And so all you need to do is say set tracing on in SQL Shell, and then it will trace subsequent statements until you turn it off or disconnect your session. So here's an example of doing a trace across a simple insert in a cluster with, I think this was a 3-node cluster, but I only had to touch 2 nodes because I have just a single replica. So I start off in blue. This is my coordinator node that received the request. The request of just insert into this table something simple. So the coordinator request says, hey, I'm going to send that to the replica, which is .2. .2 says I got the request, I'm applying the write, and then it acknowledges back to the coordinator that it was successful. So really simple request here just to illustrate how that tracing works and how it can pull together the information that even across the cluster, across multiple nodes being involved with the request. So let me illustrate something that's a little bit more real world. So here, what I'm going to do here is I'm going to show what happens when I trace some requests across this queues table. So one of the things that people are sort of incentivized to do when they learn about Cassandra and how it gives you pre-sorted partitions of data, is they say, wow, a pre-sorted partition of data, that looks an awful lot like a durable queue. So people start to use Cassandra like that, and so they'll have a data model that looks something like this, where I have a queue ID, and then I have some events in the queue that I have each event has a creation time and a value. And so since I'm going to create that with the primary key of the queue ID and the event creation time, so that tells Cassandra I'm actually going to sort each of those partitions denoted by the ID. I'm going to sort each of those by creation time. So that kind of gives me a chronological queue. So I start inserting items into my queue, events into my queue, or what have you. And then when I go to read from this, the first event that I want to read is really efficient. It's really, I just have to go to the beginning of the partition, there's my row that I wanted, pull it off. But what happens as I start pulling off events and deleting them and pulling them off and deleting them, I still have to scan through starting at the beginning of the partition for that next event that hasn't been deleted yet. And so what you end up with is a query, that trace that looks something like this. So here's my give me the next event query, select from queues, order by created at limit 1, right? So very, very standard, should be very straightforward. I look at the trace though, everything's small number of microseconds until I get to this line where it says I read 1 live cell and almost 20,000 tombstone. So where this is coming from, so to set this up, I inserted 10,000 events into the queue and deleted all but 1. So I'm asking for that last one after deleting 9,999. So you see that number there is exactly 9999 times 2. So what that's saying is I had the original 9,000 plus entries, and then I also, when I went to delete them, I inserted an additional 9,000 plus tombstones. And so Cassandra is merging those entries with the corresponding tombstone as it scans through that partition. So that's what's going on. So most people in this room, I don't expect to have that knowledge of Cassandra internals, but that's kind of the point, is that having the tracing at least gives you, it says, okay, here's my smoking gun. This is what's taking so long. And well, this 20,000 number there, that looks really weird. Where is that coming from? Why is that number so large? Why is it having to scan through so much? And so then you can start to dig more into what happens when you delete rows and so forth in Cassandra. So this is my favorite thing to do now when there's a performance question on Stack Overflow with Cassandra is, can you post a trace that illustrating the offending behavior? So we also had some operational level improvements in 1.2. I've mentioned some of these before. Should I raise your hand if I should go over virtual nodes? Okay, so I've got a fair number here, so I will do that really quick. So in classical Cassandra, which is to say Cassandra up until 1.1, and also by default in 1.2, each node in a Cassandra cluster gets a single token. And we use that token to do consistent hashing on the rows that you give us to decide what replicas they should belong to. So what we do with virtual nodes is we're going to take that single range of responsibility that a node has on the token ring, and we want to split it up and distribute it across the token ring. And what that's going to do for us is it's going to mean that instead of this machine here just sharing replicas with the machines that own these other tokens, now I'm sharing replicas with the machines that own these, and the machines that own these, and the machines that own these. So basically, I'm spreading out my replication for a given machine across the entire cluster. So that lets us do a couple powerful things. One is that when I add new nodes to the cluster, I'm assuming that I'm streaming data, smaller amounts of data from every existing machine in the cluster. So instead of just streaming a large amount from one machine, I'm streaming a small amount from the entire cluster. Similarly, when I go to rebuild a machine, I can parallelize that a lot better as well. So to illustrate that, if I have my cluster that doesn't have vnodes enabled, so I've got one token per machine, and I lose node 5, node 5 has replicas of ranges C, D, and E. So I need to find a replica of each of those ranges and pull them into the new replacement. So what I'm getting there is I'm able to parallelize that across the cluster by my replication factor. So if I have 3 replicas of each row, I can pull I can pull data from 3 machines in the cluster when I'm doing my rebuild. So that's great when I have 6 machines in my cluster, as on this slide. So I've got a 50% participation rate. That's not too bad. But when I have 100 nodes in my cluster, a 3% participation rate is not so great. So when I enable vnodes, now each machine's token ranges are split up on a much finer grained level. Now I can pull parts of the data to rebuild. I'm pulling each of those sub-ranges from a different machine, so everyone gets to participate. So you can see as you start to have multiple terabytes of data on one of these machines, how being able to parallelize that for a rebuild starts to become increasingly important.
Can you run these vnodes on just one machine in separate JVMs, so they're separate, like separate systems all on the same node?
Short answer is no.
Okay.
So you can kind of manually do that, and I've seen some people do this in the pre 1.2 days, and I'll show you what limitations they were running into that would make them run multiple JVMs on a machine, each with their own token. But under 1.2, we've made some improvements to the storage engine so that basically having a single JVM process is no longer a bottleneck. So,
okay.
Yeah.
Well, we were sort of interested in looking at, it's not really running it in multiple JVMs, but we want to be able, we have like a really fat nodes with a lot of disk hanging off, more than what y'all can handle at a node. And it's like we're trying to figure out, well, how can we use all our disk at one node? And that's why I was wondering if you could have like separate JVMs and then have each JVM have its own file system for its processing. Alternatively, we might just set up some VMs at the fat nodes, but.
So let's go about 10 more minutes,
okay. And
I'm going to talk about the improvements we've made to allow Cassandra to address lots more disk within a single JVM. Okay. And if that doesn't answer the question, then let's go into it in more detail.
Okay. I just want to clarify, excuse me, one thing I heard you say a couple times, which is every node would participate in the rebuild of a node. And wouldn't it be just still a subset, but maybe a larger subset, depending on the number of virtual nodes per node?
Yeah, so technically, yeah. So by default, if you enable vnodes, it's going to come up with 256.
Oh, okay.
So
unless you have a really big cluster.
Yeah, so unless you have a really big cluster, the odds are extremely good that you will get one from each. But technically, since you assign random tokens to each of the vnodes, technically it's possible that maybe I'll leave one machine out. But yeah, we pick a fairly large number of vnodes to make that likely that you do get a large degree of participation. So here's where we start to talk about. What's your name?
David Boney.
What David was referring to about the limitations of earlier versions of Cassandra in addressing large amounts of data on disk. So just as a refresher, since Cassandra is a Java-based system, to a large degree, we are bound by how much data that we can put on the JVM heap. And the JVM heap is limited to about 8 gigabytes in terms of what it can handle before you start hitting unacceptably long garbage collection pause times. The problem is that most modern machines are going to have much more RAM available than that 8 gigabytes that the JVM can reasonably make use of. So to have a effective storage engine, we need to be able to make good use of this off-heap memory as well. And that's part of the story for 1.2 and 2.0. So to illustrate what the parts of the storage engine that I'm going to be talking about that we've been moving off-heap, I'm going to go over really quickly what happens when you ask for a row. You ask Cassandra to give you a certain row. So we're going to start off by looking at looking at a Bloom filter that contains the partition keys for every data file. And so what I'm going to do is if I ask for a row in a given partition and I don't have any entry for this partition at all, then I'm done. I don't need to touch disk at all. This Bloom filter is in memory, so that's important because we're memory limited on the JVM heap. And so I've got this line here on my slide. Everything above this line is going to be in memory, and below the line is going to be on disk. The next thing we're going to touch is the partition key cache. So the Bloom filter said, okay, I probably have data for this partition. The key cache tells me, okay, where on disk is this partition located? So I'm going to check that next. If I have a hit in the key cache, then that's going to give me back a partition summary entry that tells me within the partition, here's where the rows are that you might be looking for. So if I, sorry, I explained that incorrectly. If I get a partition key cache, we're going to skip, if I get a hit, we're going to skip over to this end, and we'll get to that in just a second. If I miss, then I have to go look in the partition summary to find out where that partition actually begins, and then I put that into the cache for the next read to come along. So after I read the summary entry, then I need to go to the partition index, which is located on disk. So all these parts so far, these have been in memory, but this part's on disk. So that's my first seek on disk, potentially, to go and access the index of partition entries. Once I've got that index, then I go to my compression offset map. So Cassandra has had compression enabled by default since I think 1.1 and enabled optionally in 1.0. So what this is saying is, as I streamed out my data file to disk, I was recording what offset in the compressed stream corresponded to my uncompressed input. So all of these are storing uncompressed offsets. So the compression offset map is going to let me turn that into what it is on what block of compressed data I need to pull in. So that's why if I have a key cache hit, then I skip to looking up that offset in the compression map. And then finally, whoops, dang it. And then finally I can pull that data row off of the disk. So these entries here in memory are what consume a large amount of that 8 gigabytes of heap that we have available. So in 1.2 we've moved the two biggest ones off heap, and in 2.0 we moved the last one off heap as well. So the Bloom filter is 1 to 2 gigabytes per billion partitions. The compression metadata is 1 to 3 gigabytes per terabyte compressed. And the partition summary is not quite as large, but we've moved that off heap in 2.0 as well. The last one, the partition key cache, that's actually a bounded size. Since it's a cache, you can just tell it, I want you to use 1 gigabyte of memory for the partition key cache, and then it won't exceed that. So you don't need to worry about that growing uncontrollably. But these other pieces, the reason why they're problematic is they all grow linearly with the amount of data that you're storing. So that's why 1 terabyte was basically the maximum that we'd recommend storing on a Cassandra instance on its own. So we increased that by an order of magnitude by moving all of this data off heap.
So that makes lots of sense, I think I understand. I just have one question about the Bloom filter. As you do inserts and deletes, do you need to rebuild that filter periodically? Or
so so this is actually, this is per data file, all these structures. So when I stream out a new set of updates, then I create a new Bloom filter for that set that I just wrote. And then when I go through and I perform compaction and I combine it with earlier versions of data from those rows, then I will rebuild a new Bloom filter for that compacted data file. So the downside, so like David said, one of the workarounds that people would use in earlier versions to access larger amounts of data on a Cassandra machine would be to split up into multiple JVMs. So that gives me effectively a lot more heap available by having multiple JVMs running it. The downside is though that you really need a separate spindle for a commit log for each instance that you're running. So if I have 8 disks and I have 4 instances running, that gives me basically 1 commit log disk and 1 data disk per instance. And so I'm basically losing 50% of my disk to commit log spindles. Whereas if I have one instance, then I only need one commit log disk and 7 data disks. So I get a much better efficiency that way.
So how much data can you store at one node now?
It does depend a little bit on the distribution of the data. For instance, the Bloom filter, that grows with the number of partitions you have, but the compression offsets grows with rows times columns. So it varies a little bit, but 5 to 10 terabytes is what is our rule of thumb.
So how does the path change if compression is disabled? You just go directly?
Yeah, if compression is disabled, then everyone skips this step and knows where to grab it from disk. Generally speaking, though, and the reason we turn compression on by default, generally speaking, it's a win, even though I have basically an extra hash table lookup, because my disk cache, my disk page cache, is that much more effective.
When you say off heap, it's still in memory, right? It's just in NI or something.
Right, right. So we're basically doing malloc and free to make the garbage collector not mess with it.
Are you doing unsave?
Yes. Okay, so almost done with 1.2. One of the last things we did in 1.2, and this actually happened in 1.2.5. So again, we kind of slipped a feature in the middle there, is compaction throttling. And so part of the reason why we felt good about slipping it in the middle was that we've been advertising throttling, compaction throttling since 0.8. The problem was it didn't work as advertised. So what I mean by that is, compaction throttling means telling Cassandra, I want you to do X megabytes per second of I/O on compaction and leave the rest to make sure my application reads are getting served up quickly. The problem is that it would only throttle on partition boundaries. So what it would do is it would compaction full speed ahead, finish a partition, then say, oh, I've been going faster than my allotted throughput, so I'm going to stop for a while to make my average what it's supposed to work out to be, then full speed ahead again, then stop for a while, then full speed ahead. So really, it really wasn't delivering on the design goal of smoothing out that disk utilization. So for 1.2.5, we kind of went a bit lower level than the partition loop in the compaction logic, and basically put a rate limiter inside the random access filed subclass that we're using there to smooth it out a lot more, irregardless of where the partition boundaries are. I'm sorry, regardless. For the pedantic grammar Nazis in the audience. So that brings us to 2.0. For 2.0, we have a shorter list of improvements, but architecturally, they're more significant. So the first one is lightweight transactions. And so Cassandra, under the hood, whether you call it eventual consistency or tunable consistency, it's a system that's designed to avoid having operations need to wait for each other. We're really allergic to locks or any other structure that makes one machine have to coordinate with another machine to process an update. So that's great for a lot of applications. In fact, over the past 3 years, we have a lot of experience showing people how to architect just about anything on top of that paradigm. But there's certain operations that you just can't get around it. You really need to have linearizability operations. Or in the relational world, we'd say we need a serializable isolation level. So, for example, if I'm allowing people to register for my application, so I might have a logic that looks something like this, where I'm going to check, does does this user already exist? If it doesn't, then I'll go ahead and create it. So the problem is that if I have two sessions running this same logic concurrently, whether it's on different machines or different processes, whatever, just to make it a little more clear in your mind, you can picture these as happening in different data centers if you want, so that it's clear that having cross-data center coordination for every operation is a non-starter. So maybe that lets you see how if I'm doing this at the same time in different data centers, then one of these is going to stomp on the other. One of these is going to do the insert, but even though Cassandra told both of them it doesn't already exist, so they both try to insert, only one of those actually wins. So our initial thoughts around solving this problem revolved around doing some kind of locking. And this evolved out of kind of the community's practice of saying, well, Cassandra won't let me linearize these operations, so I'm just going to slap a big distributed lock on top of it with Zookeeper, for instance. That's a common choice. And so if I make each session here grab a lock on the JB Ellis row before proceeding, then I've effectively linearized things. The problem is that this works great as long as nobody crashes. If I crash, if I have a replica go down at that phase of doing the insert, I'm inserting the new user. What Cassandra will do is it will say, okay, the replica went down, so I'm going to write a hint to make sure that I replay that update later. So now what do? Is the lock holder. You basically need to hold that lock until the hint gets replayed. So you have no idea how long this machine is going to be down. So holding that lock indefinitely seems like it's a sticky situation. You can't give up the lock correctly. You can't maintain correctness if you give up the lock, but maintaining arbitrary numbers of locks indefinitely is generally not a good thing to do in systems design. So we went back to the drawing board and we settled on using a Paxos-based approach rather than doing any form of locking. This has several good qualities that make it a good fit for Cassandra. One of the big ones is that all operations in Paxos are quorum-based. So there's no, you can still lose up to a majority of your replicas and still be able to make progress. So that's good for us because we don't like processes that require all replicas to be alive all the time in a Cassandra cluster. Because if you require that, then when you have dozens or hundreds of machines in your cluster, someone's going to be down, and you can't afford to have that bring your whole application grinding to a halt. So having that quorum-based kind of fault tolerance was attractive. You can think of Paxos as kind of a two-phase commit on steroids, and one of the key concepts there. So in two-phase commit, you have a leader, and he says, "Hey replicas, prepare this transaction." The replicas say okay, or they say no. If everyone says okay, the leader then says, "Okay, let's commit," because everyone said they were good to go. So there's a bunch of problems with that and ways that two-phase commit can get wedged, particularly if the leader itself goes down. One of the key differences, key improvements that Paxos makes is that each replica sends any information about unfinished operations it has to the leader. So if the leader proposes a change in Paxos, then it dies. The next leader to come along, he'll propose a change, and the replicas will say, okay, that's nice, but first, here's this unfinished change that got proposed by this earlier leader. Let's finish that up and either drop it on the floor or finish it up before we move on. So it gives you that kind of resilience as well. Paxos has a reputation of being very difficult. A lot of that has to do with, well, a lot of it has to do with trying to make it fast as well as correct. We've settled for making it correct. And so that simplifies things a lot. And there's a paper called Paxos Made Simple that's actually a really straightforward, clear explanation of this. So I said we settled for making it simple. And so doing a Paxos-enabled lightweight transaction in Cassandra is going to require 4 times as many round trips as a normal, just here's the write, go make it happen update. So this is clearly something, and I have a whole slide on this, use with caution. This is clearly something that you don't want to build your entire application around, or the performance penalty is unacceptable. It's for that 1% of your application that you absolutely need, only one of these operations happening at a time. It's actually linearized per partition, so it's not one at a time across the cluster, but one at a time per partition. And we've introduced a new consistency level .serial, that lets a read come along and say, I want to know what the latest version of this column is, even if it's part of the uncommitted Paxos state. So I went into a lot more detail in a blog entry that's linked here on how this is working under the hood. Yes?
Well, if the leader goes down before it says commit, and one of the replicas responds back to a new leader and says, wait, but we have these unfinished items of business.
Right.
What does that new leader then do if it doesn't know about that previous state?
It basically, it looks for, so this is a good question. So you use Cassandra?
Some.
Yeah, so normally, normal Cassandra operations are purely timestamp based. So if I have if I have a single copy that says, a single replica that says, I have a timestamp on this operation of 1000, then even if there's 5 other replicas that say I have a different value at timestamp 100, the single value at 1000 wins and says, hey, you guys must be wrong, I have a higher timestamp, so fix yourselves. So Paxos is different. Paxos actually looks at how many replicas agree on a different state. So if the leader went down, the next leader to come along would actually say, do a majority of the replicas acknowledge this proposal? And if they do, then it says, okay, well, any other replicas, get yourself in line with these other guys and everyone commit. But if it doesn't, then it says, okay, sorry, replica who's odd man out. Everyone else says that wasn't interesting, so we're just going to move on with the next proposal.
So it will have a blatant disregard for timestamp at that point because it's just picking quorum based?
At that level, yes. And so the reason I say at that level is that we actually use timestamps to generate the Paxos ballots. But go read Paxos Made Simple if you want to get into that level of detail.
Just a really quick digression, hopefully. I was talking with someone about how I think it's maybe Mongo or React, but it doesn't use timestamps, but instead uses some sort of shared counter for conflict resolution.
That's a completely different topic. Someday I will write a paper about why your distributed system does not need vector clocks.
Who generates the timestamp?
Exactly.
We don't have to talk about it now.
All right, so what time is it, Nick?
So you don't need to sit
We're supposed to be here till 8:30, right? So
We got time.
So we're good.
I don't need to check what time we have.
All right. Well, it was on my calendar as until 8:30, so we're unofficially good until then. So okay. So suppose we have a cluster, and we'll just have a 3-node cluster to keep it simple. And across this 3-node cluster, we have 3 replicas of each piece of data. So every node in the cluster is replicating every piece of data. So kind of the simplest possible distributed system. Now, let's see, what might be a good example? Okay, so suppose I have some strange Twitter implementation where I have my users table and I have my user ID and I have a map of direct messages. So I have a map of other user and, sorry, that wouldn't work. So my users are UUIDs. So I have a map of another user to a message. So obviously I'm making this up on the spur of the moment. This isn't a this isn't a very realistic example, but I think it illustrates the problem. So now suppose that there's a network partition. So that there's, some of my friends are talking to nodes on this side of the partition, and some of my friends are talking to nodes over here. And two of my friends want to send me a direct message. So they'll both say insert into users, user ID, comma, I didn't give this a name, did I? We'll just call it direct messages. Direct messages, and we'll say values, whatever my UUID is, and Josh is sending me a direct message. Hi. So Josh says hi over here, and Sam says hi on this side of the partition. Let's call this the direct messages table. That's going to work a little better. So I've got, on each side of the partition, I have a single entry in the direct messages table, but they're different. So a vector clock-based system, so now the partition heals. Everyone can talk to each other again now. So a vector clock-based system would say, when I say select star from direct messages where user ID is JB Ellis, a vector clock-based system would say, here's the two values. Here's the two rows. Figure out what to make of that. And so Cassandra says that that's a bad approach. I shouldn't push conflict resolution out to the client like that. If you look, REAC is probably the most notable system out there that uses a vector clock approach. And so they call this situation siblings, that I have multiple versions of a document that I need to combine somehow. And to a first approximation, about half the talks at the last recon were about dealing with siblings. It's a really painful thing to do in the general case. You basically have to write client-side logic to deal with that. So REAC is actually taken, by default, it uses last write wins. So there's each of these nodes is generating timestamps, and hopefully they're reasonably well synchronized. We'll just pick one of those and say, okay, this other update doesn't exist. One of them wins. There was something else I wanted to say about that, but maybe it'll come to me. Cassandra, though, says that, yes, we always have last write wins, but remember what I said earlier about the email addresses set update being more efficient in Cassandra because we're not having to rewrite the entire document. The same thing happens with conflict resolution. We resolve conflict on a per cell basis. So since I have different users sending me direct messages, these don't conflict. I'm able to resolve this into a 2-entry map without having to throw anything away. So this is why if you look at kind of second generation systems that were inspired by the original Dynamo vector clock thing, Cassandra, DynamoDB, which is Amazon's productized next generation Dynamo. There's at least one other on that list. I'm forgetting it now, but if you, they all said that, well, vector clocks, that was one of the ideas that didn't actually work out as well as we hoped. So let's do conflict resolution differently, but without inflicting vector clocks on people. So if you look at DynamoDB, it's actually a very Cassandra-like system where you have kind of primary keys and then you have sub-keys within a document, and those sub-keys can be reconciled automatically without throwing it out to the client. So that's the short, unpolished version of why you don't need vector clocks if your data model is designed correctly and your storage engine, is field or cell-based rather than, I just have a single atomic document that I don't know how to peer inside of and merge at a more finer grain. Okay, so back to lightweight transactions. This is what it looks like in CQL. There's two forms, one for insert and one for update. The insert one's really simple. It's just adding the clause if not exists that says I can perform this insert and it will be linearized with other people trying to do a transactional insert, and if nobody else is doing it, then I win, and there you go. Otherwise, what it will do is it will kick back out to you and say, here's the row that was inserted that you lost the race to. Now, what do you want to do? Do you want to update it, or do you want to try a different username, or what have you? It's up to the application at that point. Update's a little more interesting because here I'm saying the row, I'm presupposing that the row exists. So I'm saying perform this update on the row if some combination of predicates. So in this example, the column I'm updating is the same as the column that I'm doing my if clause on, but that's not required. So I can check some set of columns and then update completely different columns. So I can have a bunch of ands here on the if clause. I don't do ors, but I can do and.
For that first example, if somebody else inserted the same row but a different set of columns, and you were saying if not exists and you're trying to insert the same row but there's a distinct set of columns from the other session, will they both apply the same columns? Does that make sense? So like if you have email 1 and email 2.
Let me think about that. No, they will still conflict, even if I'm inserting different columns
So
in
just at the row key level, purely.
Conceptually, yeah. Yeah. One thing that we haven't quite figured out the syntax for is the underlying engine is actually capable of updating or modifying different rows in the partition here than I'm checking here. So I can check one row and then modify another row, a different row, as long as it's in the same partition. So that's actually one place where we've kind of gone a little bit backwards, because you can actually do that from Thrift, but you can't do it from CQL yet. So we're going to fix that. Don't worry. Yeah.
So what is the difference between the syntax if email equals to something as opposed to where username equals to this and email equals to whatever?
So this is saying, so without this, just look at the part above the if. That's saying, here's what I want you to change. I want you to change, and the where says, change this row.
Right.
And so the if is saying, change this row if some columns in this row match what I expect.
But that is different from where row key is this and some column has this value. Like, I mean, isn't it the same thing, what we were saying, at least that syntax?
Let's see.
Or is there any subtle difference there?
Well, so the row key uniquely identifies the row. So if I had yeah, I get what you're saying. So coming from a relational background, it's a little confusing. To clarify, to Cassandra, you can't do that. So I couldn't say update user, set email equals X, where username equals JBLS, and email equals X. So the where only, you can only give it a primary key. And there's some caveats there with involving in, but that's the basic idea. So yeah.
Is there any consideration in being able to collapse those two into an upsert or merge command in the SQL language?
Yeah, so just leave off the lightweight transaction business and everything's an upsert.
I'm new to this as well,
yeah.
admittedly.
Yeah. Yeah, so I skipped some of the basics tonight, but yeah, everything's an upsert.
Can I ask one other question on that? And when it comes to that, can you have the upsert that does the addition of, that will do the addition of collections, like inherent in the upsert command?
Not 100% sure what you mean.
So, and I can ask you afterwards if we're running over, but when you say that there's collection types and you can have in that just in one command the addition of a collection with an existing collection
right.
to the new.
Oh yes, yeah, you can yeah,
can
that's an upsert too.
Very cool. Thank you.
So we've also added triggers in 2.0. That's so changing directions a little bit here. I guess I can pause and ask, are there other questions about lightweight transactions? Because I'm done talking about them otherwise. Okay, good to go. Okay, so triggers, creating a trigger looks like this. And so you see the class name here. This is a very, this is a kind of an experimental feature. So we're giving you a very raw API where you have to write Java classes to implement a trigger. On the upside, that does give you, the maximum amount of power possible. So you can use a trigger to emit a storm tuple or to send an email message, whatever you want to write in that Java class, great.
The trigger doesn't have any logic of its own. It just sends every single thing to the Java class to filter it
basically,
on how you want to do it.
So here's what that looks like. I have an iTrigger interface that has a single method called augment. So for augment gets called with the partition key and then the row being updated, and then it can do two things. First, it can execute arbitrary Java code, but what it can also do is it can return a collection of changes saying that, okay, based on this change that happened, I went and I read some other data, and I want to now insert 4 other rows based on that change that was made into other tables.
Is this spun off like in a separate thread so that, like, when you pass it over to the class to do stuff, it can take a while and come back and not affect what's going on in this thread in terms of
the triggers are deliberately synchronous because and the reason is, so you're welcome. So it's Java, right? You can start a new thread there if you want.
Okay.
But the basic trigger is synchronous because a common case is I want to make these other changes to other tables based on what I'm inserting or based on what I'm updating, and I want that to be atomic. So one of the few guarantees that I'll give you is that the changes that you give me back from this trigger is I will make those changes atomically. Now, atomically doesn't mean all at once. It means that if part of it happens, all of it happens. So I'll still potentially be able to read 2 of these rows before the other 5 have been written out. But I will either see none of them happen because the coordinator died right after the trigger method got called and nobody got inserted. But if anyone gets inserted, then everyone will.
But you do still have potential for race conditions, depending on timing.
In which sense?
So like, if our trigger were going to update table B, and also table C, and meanwhile some other thread operation is also updating one of those tables, depending on the timing, that other operation may or may not win the race to update.
Yeah. So it's still an eventually consistent system, right? And you could probably put some lightweight transaction here if you were if you were familiar with the internals. But fundamentally, yeah. I mean, don't try to. It's not meant for building relational style long transactions that chain off of each other. It's really more what the method says. I want to augment this change with a batch of others, or I want to send a notification out to my Kafka queue or my Storm topology or whatever.
So would this be good for keeping up to date, like a secondary index, maybe an Elasticsearch or something along those lines? Or?
Yeah, the example that we ship actually. So in the source tree, there's an examples directory. There's an example. Do a toy distributed index using triggers. So,
what's the overhead? Let's just say you had a simple class there, a do nothing class that just you call it and it returns. What's the overhead from the trigger infrastructure when you set the trigger on the table?
All of the reflection is done at startup time, so there's no reflection going on in the critical path. So a no-op augment method is probably going to be JITted right out.
Just so I'm clear on what atomic means there, like, in case you have a right to your primary index or A, and every time that happens, you want to write to your secondary index B. If you have the right to A, you have a trigger, and the trigger throws an exception. What happens?
Then nothing gets written.
Nothing gets written.
Right,
because if I get back A something.
I think we have an internal error exception to send back to the client. So yeah, so that's why they're synchronous, right? So that lets us preserve that atomicity guarantee. So yeah, like I said, it is experimental. We're probably going to change the API as we get more experience understanding what the use cases are that we should be designing for here. Yeah, but there's enough people that. So the background is, let me take a step back and give a higher level view. The background is that in a relational world, people were said, oh, triggers will push the logic to the database. That's great. Now the application doesn't have to maintain that logic, and you can have lots of people calling into the same database, and the database will make sure that everything happens the way it should be. And that was going on in the late 80s. And then into the 90s, people realized, oh wait, my database is my single point of performance bottleneck, and so I really want to push everything out of the database and into the application tier because the application tier is stateless, so I can scale that really easily just by sending more machines. So with Cassandra, we've kind of come full circle that now I can scale the database as well. So there's no reason now for me not to move logic close to the data when that's what makes sense. And so that's what's driving. So the people who are excited about this are the people running 100-node Cassandra clusters, and they're saying, it's worth a little bit of pain in the ass factor for me to save a few tens of machines worth of performance. So that's kind of what's driving this. Questions? Do we have time for questions? Nick's looking at me.
We got it till 8:30, so.
Okay.
So when you add this trigger, it's distributed across all the nodes.
Right.
And then once you're done, then it'll say yes.
Well, basically, so it's a little more primitive than that. First, you have to put the jar file on all the nodes.
Okay.
So that's your job. And then you,
Okay.
The jar runs in the server space, so if the jar crashes, it could crash the JVM.
Yes, so don't do send.miss.unsafe in your trigger code. That's what I would suggest. But you know, if it just throws a Java exception, then it just takes down that thread, so everything else goes on.
You mentioned a lot earlier about the rate limiter, and I've noticed, so a lot of times I try to fill Cassandra with my data that's been processed from Hadoop, which I know is not ideal, but I've noticed that it'll get overloaded a lot because it'll fill up the whole JVM and it fills up the whole journal and it just can't handle anymore. Like it'll start saying overloaded, overloaded, and the machines start going up and down. So I've kind of had to implement a rate limiter on my side, but I have been using your Java driver. Does it support the rate limiting stuff? Like, how do I make sure I don't send too many writes to the point where I start causing my nose to go up and down?
I don't actually know what our Java driver does there, because the best practice is when Cassandra gives you a timeout exception, then slow down. So I don't actually know what it does if it tries to automate that. So if you send me an email, I'll be happy to follow up on that. And,
It's got an incremental back off in there, I think.
Yeah?
Yeah, I think.
Probably.
Yeah, I mean, it'll still work, don't get me wrong. It's just, if I don't push it so hard, it actually handles it a lot better.
Right.
Speaking of Hadoop, have there been any changes in Hadoop integration? I think I noticed a word Hadoop on one of your slides.
Yeah, so we actually wrote, so the original Hadoop input format that we had operated at kind of the thrift level of raw, you know, partitions and cells within them. And so we created a CQL-aware input format called CQL paging input format. And basically, it allows you to give it a CQL query and turn that into a MapReduce job that gives you, so you know, MapReduce is all about the key value, right? So instead of the value being a whole partition of data, like with the old input format, now the value is a row of data. So that makes a lot more sense in the CQL world.
And is that 2.0?
That's in 1.2.6 or 7. So recent 1.2s.
So when are y'all going to put Cassandra 2.0 in DSE?
We're working on it concurrent with the 2.0 release, and so we just had the DSE 3.1, and we're looking at 4.0. 4.0 will have 2.0 in it.
Is there a date or?
Do you know if we're saying anything publicly on that? We're not announcing a date.
Thanks.
No. We have an internal goal, but I guess we're not putting it out there yet.
Q4.
All right. Well, see, Q4, that's coming up soon, right?
Before the end of the year.
Yes.
Depends on what your quarters are.
And what fiscal year.
So if I don't need transactions and triggers sound interesting but kind of scary, what would you say is my motivation to look at moving a 1.2 project to 2.0?
We got rid of super columns.
Completely got rid of them?
So we got rid of them internally, but we still translate the super column API into composites internally, and we translate that on the fly for you. So actually, that was kind of more of a joke. Sorry.
Okay. That was a pretty ghetto code path, though.
What did we change in 2.0 that we enabled vnodes by default?
Tracing kind of one.
Tracing's 1.2.
Can you index?
I'm sure there's things we made more performant.
Your off
we usually get some of those in. What's that?
Your off heap stuff? Is it too
So we did finish moving the partition summary off heap in 2.0. So that was still on heap in 1.2. What was my other list of highlights in 2.0?
Can you do?
Those are pretty highlightful for me, but compaction one might make you care. So we have level compaction and size tiered compaction. And for read-heavy workloads, we typically recommend level compaction. And the problem that you tend to get into there is kind of what the gentleman in the black shirt was referring to, although that describes several people in the room, but the one in front of you. What's your name?
Logan.
Logan? What Logan was describing where you can get when you get overloaded, and then if you keep throwing stuff at it while it's overloaded, then it tends to get more overloaded. And you see this in the leveled compaction particularly, where L0, the unleveled data fills up, and then so that makes my read slower, so I have less throughput available to compaction, so my level 0 gets bigger still, which makes reads even slower, so I have this vicious circle. So what we did in 2.0 is we actually, once level 0 gets more SS tables in it than it is allowed to compact in a single pass, which is 32 by default, but you can configure it. Then it will start performing size-tiered compaction within L0. And so what that does is it doesn't magically make compaction faster, but it will keep reads from deteriorating as drastically until compaction can catch up.
Can you do secondary indexing on collections?
Not yet.
Can you do Solr indexing on collections?
That's out of my jurisdiction. Nick's shaking his head.
Pretty sure the answer is no.
Okay.
I would have guessed yes, because it seems like it should be a straightforward mapping, but Solr is kind of a strange hydra to deal with.
Take
so
my word on that, absolutely.
yeah, we'd have to get back to you on that one too. We don't have a Solr expert in the room, I don't think. And then to finish answering your question, the last one on the list here, the cursors, that could actually be a big reason to upgrade, depending on what your application code looks like. But what that does is it's like a relational database cursor, where I give you this query that returns thousands of rows, and then you pull back those rows as needed without having to manually page through the result set.
Did you cover eager retries? I don't remember.
I didn't. I skipped that because it takes a whole lot of diagrams. But I can do it on the whiteboard real quick. So what's going on there?
Sorry, could you repeat the question?
And for the benefit of the video, the question was, what are eager retries? So if I have my cluster again, and in this case, we're going to have 2 replicas, because it's less interesting if there's 3. So let's say that I have the client over here. He's talking to the coordinator, and the coordinator doesn't have the data I'm looking for. So that's important to the example. So the coordinator, so we've got a bunch of infrastructure internal to Cassandra to try to route the request to the replica that's best performing. Somewhere along the line, I think it was in 1.2, the nodes will actually gossip when they're busy with compaction, and so that will be a signal to the coordinator. Well, if he's doing compaction, he's probably not going to be super fast, and so I'll try to direct the request elsewhere. I'll also look at the performance of the request that I actually make, and route future requests based on that as well. So suppose I make a request to this replica, and then maybe a compaction starts, or maybe the node just dies entirely, and I don't get an answer back. So under 1.2, Cassandra would say, timed out exception, sorry, didn't work out, better luck next time. Under 2.0, what it will do is the coordinator, after 75%, after the point at which 75% of requests have successfully completed, it will say, okay, well, you're taking longer than usual. Let me make a backup request to this other replica and see if he gets me the data faster. So what I'm trying to do is I'm doing redundant requests, but only for requests that look like they will need them. So I get most of the benefit of doing multiple requests without much of the performance impact. And so this is tunable. You can set it based on percentile, whether you want it 99.9th percentile to be super conservative, 50th percentile to be more aggressive. You can even say just screw it, just request it from all the replicas all the time, or you can turn it off and set it back to the old behavior.
What's the default?
I'm pretty sure the default is 75th, but I'd have to code dive, or probably, it's in the .yaml, so I read the comments.
Do you remember what the ticket number was on that?
I don't remember, sorry.
That's probably the first time I've heard you say it.
There's almost 6,000 tickets now, so I say that more often than not.
I'm new to Cassandra. Like, is there a concept similar to temporary tables I use in TSQL?
Depends on what you were going to use the temporary tables for.
And if I'm doing some calculations kind of thing, putting it in.
Yeah, generally speaking, no, because what we're targeting with Cassandra is we're trying to drive your application and not do analysis against the data your application has generated. And so for that kind of analysis, that's kind of what we sell with DataStax Enterprise with the Hadoop and Solr integration. And for that, part of that is a system called Hive, which is basically a SQL compiler for Hadoop. And for that, you can absolutely use temporary tables and say create table as, select from this, and join with that, and go crazy. But for Cassandra itself, we give you select from where, no joins, no create table as, no subqueries. We want you to give us a single partition of data that I can get data out quickly so that I can serve millions of operations per second.
Do you know when they'll have the Hive 0.10 version available in DSC, where you can do like the multiple connections?
This is a Cassandra talk, man.
But you brought up Hive. I mean,
sorry, I just told you everything I know about Hive.
How many columns can I have before it gets kind of funny? Does it matter? Globally?
Thrift columns or CQL columns?
Both. What's the difference between those two? Now I'm really curious.
Oh.
Didn't think it would matter.
Is it? So I don't drink, but you're tempting me.
You got 5 minutes.
All right, 5 minutes. Thrift to CQL mapping in 5 minutes. So,
I thought you could have 2 billion columns.
So, that's the distinction we're talking about here. So maybe the best way to explain it is to start, so I think in CQL now. So I'm going to give you a CQL table. So let's go with my user's example from earlier. So I have an ID, that's a UUID. We'll make this a really small table here. Give me a couple other things. Name, text, and we need a couple more. Birth, and we'll just make that an int. I think, no, we have a timestamp type. Let's make it that. Or is it date time? And what else did we say?
Tags.
Tags, sure. That's actually complicated. I don't want to map that to thrift. Let's do state. So in thrift, I would map a user as, this is actually a bad example because it's too simple. Okay, let's do some time series data. Let's do temperature. So we'll have a time data point. We'll make that a time UUID. So each data point's unique, and a location.
Yeah.
And we'll just make that text. And temperature. And should we do it a float? Let's make it a float. So what I want to do is for a given, what do I want? Should my location be my primary key? Or my partition key? location. And so I'm going to switch a little between the two. In Thrift, what I want to do is I want to have my location row key, and then I want to have basically a bunch of data points, right? So then I say, give me the most recent 100 data points. I go, whoop, there they are. So in the way we map this then is that each of these rows is one of these. So in Thrift I would have composite. I would have comparator equals composite, however you spell that, type of time UUID. I guess I don't need a composite because I just have two. Suppose I had some other data here.
Region. Sensor ID.
Employee, the person who took the reading. So I'd have a composite type, and that's a UUID. So I'd have a type UUID, comma regular UUID. That would be my cell name, and then my cell value validator equals float type. So I'm basically packing the fields, except for the last one. The last one will become the value, but I pack the other fields into a composite type. And so we've changed the terminology just a little bit to accommodate this. So the Thrift, with Thrift I'd call this a row key. Under CQL I call it the partition key. And these are my rows. And so in Thrift, I would say this is my column name, and so we've retroactively renamed that to the cell name to distinguish it from these column names that I've. So CQL is basically assigning metadata to these unnamed pieces of your composite, to the components of your composite cell name. Told you didn't want to go there.
The original question was about the limits of the width of the...
Right, so then I asked, so he said, how many columns can you have? And I said, well, are you talking about CQL columns or Thrift columns? So I'll answer both questions. You can have any reasonable number of CQL columns. And by reasonable, I mean, if I'm spending all my time marshalling up your result set metadata and saying, I have time, because every time, if I say select star from temperatures, I'm going to give you back metadata that says, okay, here's the location column, it's a text. My next column is going to be named time, it's a UUID, and so forth. So, yeah, I mean, there's no inherent. I'm trying to think of a place where we'd have a internal limit on how many you can have. Yeah, I mean, as long as you have memory to hold it in the result set, you should be okay. I can't think of any internal limits. The 2 billion number, though, that's coming from the number of cells you can have in a partition here. And so we sort of accidentally lifted that limit in 2.0. It's still not a good idea. The rule of thumb, you should probably have under 1 million cells or under 100 megabytes of data. And there's a couple reasons for that, and I think the most compelling one is that a single partition's worth of data is the unit that we repair at. So if I'm constantly appending data to this partition across different replicas in my cluster, and I say go ahead and repair this range of data and make sure everyone's in sync and has the same cells in that partition, then if even one of those hasn't been propagated to all the replicas, then it'll say, uh-oh, this partition's out of sync, and it will stream that entire partition to everyone. So you need to, 100 megabytes or 1 million cells is a good rule of thumb of how much is reasonable before you start over repairing data that didn't really need to be repaired. time.